Hello, I'm Hunter Ratliff. I'm a postdoctoral researcher at the Western Norway University of Applied Sciences. I'm from the United States, and my background is in nuclear engineering. And in this talk, I'll be trying to answer the question, is nuclear power our savior? And I'll be making the case for why I believe it's a very promising technology to guide us toward a cleaner and greener energy future. So I'll address the big concern for Norway right now, and that's its own energy situation. Norway is an extremely blessed country with an abundance of natural hydro resources. Despite being such a small country, we produce the seventh most hydroelectric power in the whole world, and over 95% of all the electricity we produce is coming from hydro. That said, as shown in the chart here, the rest of the world is not so fortunate, particularly among all the highly developed economies in the world. They can't rely on hydro to nearly the same extent as Norway. They need other more robust energy sources to fuel their strong economies, and this is where I believe the strong use case for nuclear energy is. Though Norway may also have interests in nuclear for diversifying its own energy portfolio, as well as tapping into the medical and industrial applications that nuclear has to offer. So throughout the talk, I'll be trying to answer a few different questions. I'll begin with a brief history of nuclear technology and an overview of the physics behind fission and how reactors work. Then I'll go through how does nuclear fit into our global energy mix, how does it compare to other energy sources, and answer the questions, is it green, is it safe, and what challenges does the technology face in the future and currently, and what does the future of the technology look like? So our brief history. Radioactivity is first discovered in 1896. And then 36 years later, the neutron is discovered. This is the second fundamental particle inside every nucleus of every atom, along with the proton. So 10 years after that, the Manhattan Project begins to use the neutrons to develop the world's first nuclear weapon. So by the end of 1942, we have the world's first man-made self-sustained nuclear fission reaction at the Chicago Pile Reactor located under the football stadium stands of one of the universities in Chicago. And less than 3 years later is the detonation of the world's first nuclear weapon device at the Trinity test site in mid-1945. So by the 1950s, the public is well aware of nuclear technology, but they really only know of it as this military secret used for making bombs. But the US government wanted to change that perspective. They wanted the public to see the more peaceful applications that were possible with nuclear, particularly energy production. So President Eisenhower went before the United Nations General Assembly in December of 1953 and made his famous Atoms for Peace speech, where basically he tried to demystify nuclear technology to the world and proposed an offer where America would give away its peaceful nuclear technologies under the premise that other countries would not use it to develop their own weapons programs. And this laid the groundwork for the formation of the International Atomic Energy Agency. However, the Cold War raged on, and by the late 1960s, 5 different nations had independently developed and tested their own nuclear weapons. This is the United States, United Kingdom, France, China, and the Soviet Union. And that list was only expected to continue getting longer. And the United Nations in the world in general did not want that to happen. So thus came the United Nations Nuclear Non-Proliferation Treaty. So the objective of this was to stop the spread of nuclear weapons. And this was a general agreement between the 5 nuclear weapon states and all the other United Nations signatories. All the UN members except for Israel, India, and Pakistan signed the treaty, and later North Korea would withdraw from it. But anyways, this agreement basically stated that the 5 nuclear weapon states would do their best to, over time, disarm themselves and reduce their stockpiles, and in turn, or in exchange, they would provide peaceful technology to the non-nuclear weapon states and help them out with developing their own peaceful energy programs. This also gave some force to the International Atomic Energy Agency, where now it had a responsibility to send teams to the nuclear facilities across all the signatory nations to inspect their materials and processes, to make sure that no nation was doing anything sneaky that they shouldn't have been doing with their nuclear materials. So, unfortunately, though, the United States and the Soviet Union did continue stockpiling, but by the end, eventually the Cold War came to an end, and suddenly there were a lot of nuclear weapons that no longer seemed to have nearly as much purpose as they did previously. Thus began the Megatons to megawatts program. This was a program where the United States was purchasing from Russia old Soviet warheads to downblend. So they took the highly enriched weapons-grade uranium and turned it into reactor-grade uranium and burned it in our own reactors in the U.S. So the fun statistic I like to throw around is that in the first 20 years of my life, and 10% of all the electricity I consumed and that all other Americans consumed was coming from decommissioned Soviet warheads. So now we'll get into what separates a bomb from a reactor, but before we can get into that, we need to have a quick physics lesson first. Every element is defined by the number of protons it has. For instance, hydrogen has 1 proton. However, each element can also have a variety of different isotopes, and this is defined by the number of neutrons it has. For instance, hydrogen always has 1 proton, but can either have 0, 1, or 2 neutrons. Uranium also has its own variety of isotopes, and it has one special one called uranium-235. And it has a special property of whenever there's a slow-moving neutron that gets close enough to it, it can suck up that neutron and then split into 2 smaller nuclei and 2 to 3 neutrons. And ultimately, what you have afterward weighs less than what you had before. So you've converted mass into energy with Einstein's equals mc squared principle. An individual fission releases a really small amount of energy, but then you realize just how small an atom is. So a single gram of pure uranium-235, if you completely fissioned away all of it, it would release over 24,000 kilowatt hours of energy. So with each fission comes 2 to 3 extra neutrons, and this is the key difference between a bomb and a reactor. In a bomb, you want as many of those neutrons as possible to go on to create another fission reaction, and you want the chain to spiral out of control as fast as possible. In a reactor, you want exactly 1 fission reaction to happen for every previous fission reaction. So this keeps the reaction rate constant and the energy produced constant over time. Another key distinction is the enrichment of uranium. Whenever we pull uranium out of the ground, it's only 0.7% the uranium-235 that fissions easily. So for our reactor, we generally enrich it to be about 3 to 5% uranium-235, but for a weapon, you take it to over 90%. And we're typically using gas centrifuges to do this enrichment process. One note to be made is that instead of normal water, you use heavy water, which is using hydrogen-2 instead of hydrogen-1. You actually don't have to enrich the uranium at all. You can use natural uranium, and this is what the Canadians do in their CANDO design reactor. And I'll just reiterate here or reemphasize the energy density of nuclear fuel. So a single 10-gram uranium dioxide pellet, again, which is only enriched to 3 to 5% of the stuff that actually fissions in our reactors, this single little 10-gram pellet produces more energy than a ton of coal, 1,000 cubic meters of gas, or 1,000 liters of oil. So that's how fission works. So how does a reactor in its entirety work? From the outside, it basically works the same way as a coal or gas plant or any other thermal power plant, in the sense that it's just a fancy source of heat to boil water to generate steam, to turn a turbine to generate electricity. It's just the difference here is we're splitting atoms to get that heat rather than burning hydrocarbons. All the commercial reactors we use utilize what we call slow fission or thermal fission. Basically, whenever a fission reaction happens, these 2 to 3 neutrons that come out are moving really fast, like 20,000 kilometers per second. And for the uranium-235 to more easily suck up that neutron, it needs to be slowed down a lot, to about 2 kilometers per second. And we do this by having the neutron scatter or bounce a bunch of times. Like a billiard ball, each time it bounces, it transfers some of that energy away and slows down a little bit. And we often use light element materials to do this, such as water or graphite. And this is how we slow down the neutrons, but how do we prevent those extra neutrons from creating more fissions than we want? Ultimately, we try and suck them up with other elements and isotopes. So uranium is not the only one that likes to suck up neutrons. There are plenty more that don't fission, but also like to eat neutrons. We make metal rods called control rods out of these materials. One of them is cadmium. And essentially, every neutron that the cadmium rods absorb is a neutron that can't go on to make a fission reaction. And we can control how much neutrons the cadmium rods are sucking up by sticking the rods more or less into the reactor. We can also add liquid chemicals that also like to suck up neutrons, such as boron, that can also reduce the amount of neutrons present in the reactor. There's also a concept called the critical size. Essentially, there has to be enough fissionable material in a particular geometry and arrangement for the reaction to self-sustain like it does in a reactor or in a bomb. This is why these things will react on their own, a reactor or a bomb. But a little fuel pellet or a small chunk of pure uranium-235 won't just fission away on its own. So reactors are designed with a variety of different safety mechanisms and principles in mind. The first is called defense in depth, and essentially the idea here is we put as many layers as possible between the dangerous radioactive stuff, which is contained inside the little fuel pellet, and the outside world. So the fuel pellet is surrounded in a metal fuel rod, which is put into a large fuel assembly, which is then put into the reactor pressure vessel, which itself is very thick steel. And this is all surrounded in a large concrete containment building. And all the different components and systems in a reactor are designed around what we call design basis accidents. These are essentially kind of worst case scenarios that one can imagine and are usually quite unlikely, but we design for them to withstand these accidents anyways. For instance, a containment building is generally designed to withstand an airplane crash. We also utilize passive and active safety systems. So passive systems are generally just taking advantage of the physics present to make the system safer. For example, in the light water reactors that are used in most places around the world, we're using water to slow down the neutrons. And water has the property of it actually gets worse at slowing down the neutrons the hotter it gets. So what this means is if the reaction rate is getting too high and you're producing too much energy, instead of the reaction spiraling out of control, the temperature goes up, the water gets hotter, it gets worse at slowing down the neutrons, and the neutrons get slowed down less, so the reaction rate goes back down, and the temperature goes back down, and the system kind of self-corrects. And the mechanism behind this is essentially you get little bubbles in the water, similar to if you boil water on a kettle. You see little bubbles form, and essentially this decreases the net density of the water, meaning on average, neutrons scatter fewer times between the fuel pins. Anyways, so that's passive systems where we're taking advantage of physics. In active safety systems, these are intentionally designed systems which, I guess, manually or automatically intervene, particularly in accident scenarios. So these you typically think of being what provides emergency cooling in the case that there is an accident, to keep the reactor core covered with water. And all these systems are designed with redundancy and diversity in mind. So essentially, no important system should be without a backup or multiple backups. And these systems and its backups should all be designed in such a way that a single event or type of accident couldn't knock all of them out. They should be diverse in that sense, where one type of bad accident may knock out your main system, but the backup would be fine, and vice versa in other accident scenarios. So now we'll go through how nuclear fits into the energy grid. Essentially, but first we need to talk about how the electricity grid works. Essentially, the amount of we have to produce electricity at the same rate that it's consumed. Supply has to constantly meet demand, but demand changes as a function of time throughout the day. We demand the least amount of electricity when we're all asleep, and whenever we wake up, we start turning on our appliances and our computers and whatnot, and the demand for electricity rises throughout the day. So this lets us divide the total amount of electricity into two big chunks. There's the base load, which is essentially the amount of electricity needed just to keep society afloat at all times. And then there's how much deviates above that, which is what we call the peak load. And different sources of energy or are better or worse at satisfying each of these different categories. So for our baseload sources, we want the electricity to be coming from fuels that are extremely reliable and can constantly produce a large amount of energy. This is where nuclear fits in, along with gas or with oil and coal. And these plants like to operate at a set power level, and they're quite slow and difficult to change to a different power level. They need time to either ramp up or ramp down to different amounts of power. In the middle, we have our tunable production sources. This is like hydroelectric or natural gas, where they can still produce a lot of energy, but they're also quite a bit more flexible. For instance, with the hydroelectric plant, if you don't want to produce electricity, you just don't flow the water, or at least you don't float the turbine. If the water has to flow, you can just bypass the turbine. And then we have intermittent sources like solar and wind. And these are great to have when you have them, but the sun does not always shine and the wind does not always blow. And essentially, since supply has to always meet demand, you have to have some other source of energy to supplement the intermittent sources. So you have to have more tunable sources or batteries to basically ensure that that supply can always equal demand, regardless of how much wind or solar energy is being pumped onto the grid. So this leads into another important concept, which is batteries. And this can be batteries in the conventional sense, like the electric batteries that Tesla makes, or things like gravity batteries. Like pictured on this chart is, it includes pumped storage. And the general idea with that is when electricity is cheap and abundant, you can take some of that electricity to pump water up a hill into a reservoir. And then when electricity is scarce and expensive, you can flow that water back down the hill through a turbine to put some of that electricity back onto the grid when it's more needed. But not all geographies are suited for the different types of like physical battery or water battery or gravity battery. So where does nuclear fit into the global energy mix? This chart shows the total amount of electricity produced as a function of time and from its different sources from 1985 to the present day. And we can see that essentially coal or with nuclear and hydropower have grown a little bit, but not by much. The main areas of growth have been in renewables, gas, and coal. That said, nuclear is still a substantial source or a significant source of our total electricity produced, producing just over 10% of all of the electricity across the 440 reactors in operation. An important thing to note here is that in these conversations, electricity and energy don't necessarily mean the same things. Electricity is just, as the name implies, electricity, while energy includes electricity plus the energy used for transportation like cargo ships and airplanes, and for heating in much of the world. Norway is actually a bit of an exception in this regard. We use a lot of electricity here for our heating, but in many other nations, they're still reliant on fossil fuels for their heating. So this chart shows what fraction of each country's electricity is coming from nuclear. And we see, particularly among the developed economies, it's an important source of energy or of electricity, especially in Europe. France leads the pack here with about 70% of its electricity coming from nuclear, with a variety of other countries also producing a lot of power, such as Ukraine, Slovakia, and Belgium. And our friends in Finland and Sweden are also producing quite a bit. In terms of total capacity, though, not fraction of grid, but just the total raw amount of capacity, the whole world has about 400 gigawatts of nuclear power being produced. And America is producing about a quarter of that, followed by France, China, Japan, and so on. And nuclear technology is still growing. There are a number of reactors under construction across the world using a variety of designs from different countries. So how does nuclear compare to the other energy sources? The common thing that is most praised about nuclear is its reliability, and this is coming from the metric called capacity factor. Essentially, capacity factor is how much energy does a given source produce over an amount of time, say several years, and how much could it have produced if it were operating at 100% full power that whole time? So in terms of capacity factor, solar is at the bottom because, well, a solar panel is only operating at 100% on a cloudless day when the sun is directly overhead. Well, we have night and the sun is not always directly overhead, and sometimes it's cloudy or rainy. So this means in total you're only getting about 25% of the maximum potential out of solar, at least in the US. Nuclear, on the other hand, is on the opposite end of the spectrum, where essentially these plants operate at full power all the time, and they don't really have to stop for anything very often at all. Essentially, you take down a reactor will operate for 18 months straight, and then you take it offline for 1 month to do maintenance and refueling. So the average reactor is rated to produce 1 gigawatt of electricity. So over the span of a whole year, and considering the capacity factor on average, this means it's producing about 8.2 terawatt hours of electricity per year. And this is a lot of electricity. This is enough to meet the per capita demand for nearly 300,000 Norwegians. And to produce that same amount of electricity, you would need nearly 1,000 wind turbines, over 25,000 square meters of solar panels under solar conditions that are a bit more favorable than what we have here in Norway, and about 100 average Norwegian hydro plants. So that number is a bit fuzzier because the rated capacity of a hydro plant can vary a ton from site to site. Norway in total demands about 150 terawatt hours of electricity per year, meaning it would take about 18 reactors to produce all of that electricity. That said, Norway uses a lot of electricity per person relative to other countries. We're consuming about 28 megawatt hours of electricity per person, while other countries like the US only demand 12, and countries like Sweden or Canada, in similarly cold climates, demand 17 megawatt hours per year per person. And the reason these numbers are quite different is going back to where our heating comes from. In Norway, we're using a lot of electricity for heating, which is included in the electricity statistics, while other countries are more reliant on other sources in fossil fuels for heating, which aren't counted in the electricity statistics. So how safe and clean is nuclear? This chart shows on the left the death rate from accidents and air pollution per terawatt hour of electricity produced from each source. And we see essentially that nuclear is just about as safe as wind, solar, and hydro, and all of those are literally hundreds of times safer than oil or coal. On the clean side of things, the right side of the chart shows the greenhouse gas emissions and carbon dioxide equivalent for per gigawatt hour of electricity produced over the whole lifespan of a facility. So this includes the construction, and the operation, and then the eventual deconstruction and decommissioning. So we see that nuclear is about on par, if not a tiny bit greener, than wind or solar. And those three are a bit more green than hydro, just because hydro uses a lot of concrete, which is quite a carbon-intense material. And again, they're all substantially more green as expected than the fossil fuels. But again, the point here is nuclear is standing right beside wind and solar in terms of how green it is. Cost is another important thing to consider. This chart shows the cost of nuclear and other energy sources in the American market on top and the European market on bottom in dollars per megawatt hour. So from left to right, we have the cost of new nuclear plants, keeping the current nuclear plants operating for as long as possible, followed by different kinds of solar and wind and coal, and then the big fancy gas plants that produce a lot of energy with natural gas. So we see in both markets, new nuclear is one of the more expensive options. However, in both markets, especially in the European market, keeping the current reactor fleet alive and operating for as long as possible is by far the cheapest energy source we've got. So how safe is nuclear? Again, it's about as safe as the other renewables, which are literally hundreds of times safer than coal or oil. That said, accidents do happen. The most major one of recent memory is from the 2011 Tohoku earthquake in Japan, which caused a meltdown at the Fukushima Daiichi plant. Essentially, this massive earthquake, followed by the tsunami, were both beyond design basis accidents for the plant. So it wasn't designed to be able to withstand these, but it did manage to take the earthquake just fine. And the tsunami ultimately is what did the plant in, but it could have survived if not for a very slight oversight in the design. And that was essentially the meltdown occurred because they couldn't keep the reactor core cool. They couldn't keep pumping water on top of it because they lost total power. So the electricity from around the plant had stopped working. So it was relying on its own backup generators. But the backup generators were located in the basement of a building. Had they put the backup generators instead on the roof, then the tsunami would not have flooded them and caused the backup generators, the diesel generators, to fail. That said, that's not how it was designed. So they failed. They couldn't keep the reactor core cool. So eventually the water inside the reactor core boiled off and the fuel rods became exposed. And the steam coming from the boiling water reacted with the metal that clads the fuel. And this produces a lot of hydrogen. So essentially there was a big buildup of hydrogen until eventually we had a hydrogen explosion. And this is what we all saw in the news back in 2011. While unfortunately the tsunami itself claimed, I think, on the order of 12,000 lives in Japan, the nuclear accident itself didn't kill anyone directly. That said, studies suggest that, or have estimates that there are probably about 600 deaths that could be attributed to the extra stress that the people around the Fukushima Daiichi plant had to undergo in the evacuation process, moving away from their homes and businesses. The other major accident, and by far the most significant, was Chernobyl. This accident was a combination of both a design with some inherent problems and the operators not doing things as safely or as correctly as they should have been doing. Essentially what happened at Chernobyl was it's using an old Soviet design called RMBK. Rather than using neutrons rather than using water to slow down the neutrons, it uses graphite. And we mentioned earlier that water, as the temperature goes up, gets worse at slowing down neutrons, so the system self-corrects. Graphite is actually the opposite. As the temperature goes up, it gets better at slowing down the neutrons, so the reaction rate goes up, so more power is produced, so the temperature goes up, so the neutrons get slowed down more, the reaction rate goes up, and it is a positive feedback loop. However, there were safety systems in place to prevent this from going out of control. That said, the operators were running some tests where they had intentionally disabled the safety systems, and they had also made some faulty readings as well, which ultimately led to this spiraling out of control. Now, this wasn't a nuclear explosion in the sense that you have with a bomb. Instead, this was this positive feedback loop, which resulted in a spike of power, which caused a bunch of water to evaporate in a very short amount of time. And essentially, we had a big steam explosion. There was also a secondary explosion, though it's debated whether that was from a steam explosion or a buildup of hydrogen and a hydrogen explosion. Regardless, the accident caused the direct deaths of 31 people on site, and it spread a ton of radiation, though, and this is where the most of the deaths are coming from. The World Health Organization did some studies and estimate that about 4,000 excess cancer deaths will happen in the immediate area due to the Chernobyl accident, and across all of Europe, that number will be about 9,000 or so. Though other studies, again, these things are quite difficult to estimate, and other studies suggest higher values as well. But regardless, it's on the order of thousands of excess deaths, and this is the biggest accident in nuclear history. That said, when a nuclear plant is operating just fine, it essentially has a negligible impact on your annual radiation exposure. By far, most of the radiation we receive throughout the year from natural sources is coming from the radon, coming up from the rocks in the ground, as well as from the cosmic rays showering down from space, as well as from other natural minerals and from receiving medical procedures. That said, accidents are scary. We, as humans, did not really evolve very well to handle assessing risk in these scenarios where it's a really low probability, but an extremely high consequence in the event something goes wrong. And a classic example of this is looking at people's perception of the safety of flight versus riding in a car. Most people wouldn't give a second thought to hopping in a car and riding somewhere. But about 1 in 3 people have at least some level of anxiety toward flying, with a 2.5% to 5% having a full-blown phobia of it, though the traffic statistics clearly show flight is a much safer form of transportation. So we have to keep this kind of irrational part of our minds in mind as well when thinking about nuclear, that yes, it is quite safe, but things can go wrong, similar to with an airplane. So some big challenges are still facing nuclear energy moving forward. The most high profile of these is the waste disposal problem. At the moment, whenever the fuel is done being used, it gets pulled out of the reactor and put into a cooling pool. This lets the radioactive nuclides decay away for some time and makes it, and as that happens, the amount of heat produced by that decay goes down as a function of time until eventually you can pull the fuel back out of the pool and store it in a more long-term solution. That said, we're not really doing the long-term storage very well in most of the world. At the moment, most of the spent fuel is either being moved to longer-term storage cooling pools, or, as is quite common in the US, dry cask storage. So this is essentially taking the spent fuel assemblies and placing them into a big concrete tube, which sits on a concrete pad on site of a nuclear power plant. So these spent fuel casks are still behind the security and everything and safe at the nuclear power plant, but this is clearly not a long-term solution. Some of these radionuclides live to tens or hundreds of thousands of years. And for those geologic timescales, ultimately, you need to be able to prevent and ensure that the radioactive materials won't eventually make their way into the environment. In particular, you don't want them eventually getting into the water supply and the water table. So there are several different strategies for preventing that, or making it such that the water won't be contaminated regardless of circumstance. One is called vitrification. This is essentially melting down the fuel into a glass, so the radioactive materials can't be leached out by the water. Others ideas involve creating synthetic or composite rocks made of ceramics. And another approach is called engineered encapsulation. And the idea here is, rather than melting down the fuel or changing its form factor, you essentially just take the fuel assemblies, slide them into a big steel tube, seal it off, put it into a big copper tube, seal it off, then you put it deep underground in a hole in a favorable geology like clay, and you put it in a hole and surround it with clay. And essentially, you've nigh guaranteed that water will never be able to penetrate this. And this is what Finland has done in their Onkalo repository. And Finland is so far the only nation to have permanently solved their spent nuclear fuel problem. That said, they're not the only ones because the science hasn't been solved. It's been because of politics. After all, no one wants a nuclear dump in their backyard. And as far as that's concerned, no one wants a nuclear power plant or even wind turbines in their backyard. So public sentiment and politics has been one of the major difficulties that nuclear energy has faced with time. Fortunately, the public sentiment has been improving recently as climate has become an increasingly more public and important topic. People are becoming increasingly aware that nuclear is a source of energy that's capable of producing a ton of energy and meeting a lot of our demand while not producing carbon. So hopefully the tides will continue to shift in a positive direction. Economics are another challenge. This chart shows how much does it cost to operate a nuclear plant, or how much does it cost to run a nuclear plant versus conventional fossil fuel sources and hydro. And essentially, nuclear is cheap to operate because the fuel per energy produced is quite cheap. That said, the nuclear plants are a lot more expensive to actually construct than coal or gas plants. And this is because you have to do a lot of preliminary studies and even plan out the decommissioning of the plant before you even built it. So there's extremely high upfront costs with a nuclear plant. So the general economic idea for a nuclear plant is you pay this high upfront cost, but once you've paid it off, you're essentially printing money for free because you're able to produce electricity so much cheaper than your competition. So this gets us to where the reactors are currently in age around the world. Particularly in the US and Europe, our reactors are getting kind of old. They're pushing 40 years old on average. Some are quite a bit older. And this puts us in an interesting position where the reactors are at that point where they're basically printing free money, but they're still old. They will continue to operate and be approved to operate as long as they're deemed safe, but eventually they will need to close. And at that point, each reactor is producing a ton of energy, of electricity, and we'll have to replace that with something, be it with new nuclear or other sources, and that's going to be expensive. So finally, we'll touch on what does the nuclear technology of tomorrow look like. And before I do that, I'll briefly cover how we've categorized the different generations of reactor technology. We begin with generation 1, which is the early prototype reactors, just kind of proving the viability that nuclear energy can be used for producing electricity. Then we have generation 2, which is the first commercial reactors, which are using kind of the same principles as earlier, but the designs, there's a few kind of standardized designs, but each site is still a bit of a special snowflake in its own regard, which means each plant has to be quite rigorously and separately certified. Generation 3 basically refined those designs from generation 2 and most importantly standardized them. So it became a lot more streamlined to construct and license a nuclear power plant. Then in the current generation, 3+, we essentially took what worked in generation 3 and made it bigger and took advantage of economies of scale to produce more energy at less cost per energy. Generation 4 is where we're really going to see the more innovative designs. This chart estimates Gen 4 starting around 2030. Perhaps more realistically, it would be closer to 2040, but we'll see. But essentially, the idea with the Generation 4 reactors is to improve safety, sustainability, efficiency, and cost. And we'll step through a few of the different proposed designs. So at the moment, we pull the uranium out of the ground, we enrich it, turn it into fuel, stick it in the reactor. Then once it's spent, we either, in the US, let it cool and then put it in a concrete tube and to hopefully eventually be disposed of long term. And in some countries like Japan or Korea, they take the spent fuel and they reprocess it once more to pull out the plutonium and pull out the uranium to re-enrich and then put back into a new fuel assembly to put back into the reactor to run once more. But we're still throwing a lot of good material back into the ground or away. So again, 0.7% of the uranium we pull out of the ground is uranium-235, which fissions with the slow neutrons. But the other 99.3%, the uranium-238, can also fission. It just requires the fast-moving neutrons that haven't yet been slowed down. The probabilities are lower, but it's a viable design. And it turns out that all the other heavy nuclides around uranium on the periodic table can also fission. So this includes thorium. And again, these require fast neutrons. So pictured here is one of these fast reactor designs, the sodium-cooled fast reactor. And the general idea here is we'll close the fuel cycle. Rather than pulling a bunch of material out of the ground and then putting 99% of it back into the ground later, the idea is we're actually going to be burning most of the stuff we're pulling out of the ground. And this means you're getting a lot more bang for your buck in terms of energy. And the nastiest of the radioisotopes that live for hundreds of thousands of years are generally those really heavy ones, which can also fission. So what this means is we're ultimately reducing the quantity and longevity of the nuclear waste by using these designs as well. Another design considered is the molten salt reactor. This one can be operated in this fast mode as well as a conventional thermal neutron spectrum as well. And it's touted to be the most inherently safe reactor design. In this design, rather than having solid pellets or pins of fuel. Instead, the uranium or thorium is put into a salt, and the salt is then melted, and inside the reactor core, it has this critical shape we mentioned earlier where it's able to self-sustain the reaction. But if the temperature gets too high and the reaction rate starts getting too high, eventually there's a small freezer plug at the bottom of the reactor that would just melt, and then it would just drain the liquid fuel contents of the reactor core into a large, shallow holding tank, which would then no longer be of the critical shape required to maintain the fission reaction. So the fission would no longer be self-sustained, and eventually it would just kind of slow down and re-solidify into a solid salt, completely averting a big nuclear accident where you've spread contamination. And one other design is the very high temperature reactor. The idea here is you take tiny little pellets or specks of fuel material and you embed them into a graphite ball. And these graphite balls are then put into a large volume, or what's a bed for the pebble bed style reactor. And then you flow helium as the coolant instead through here. And the helium gets really hot, like 900 to 1,000 degrees Celsius. And at these temperatures, we get some more interesting options. Rather than just being able to produce electricity, you can now use this heat to produce hydrogen through electrolysis. So this makes nuclear a flexible energy source, because suddenly when electricity is cheap, or when electricity is expensive, we can just use the heat the normal way to boil water, to generate steam, to turn a turbine, to generate electricity. But when electricity is cheap, so we do that when electricity is expensive and we make money. When electricity is cheap, instead, we can divert that heat to make hydrogen. So that can be sold and used for other energy applications, or converted back into electricity and put back onto the grid whenever it is expensive. So this essentially allows nuclear to become a tunable energy source where it's flexible. It can now follow the demand curve as a function of time throughout the day with this design. And it gives you more options if you just want to produce hydrogen too. One other design to mention is the small modular reactor. This one is a bit less innovative in terms of the core design idea than the others. It's essentially taking the best of the current generation of reactors, making something that's more inherently safe and dummy-proof, miniaturizing it, and making it in such a way that it can be more easily mass-produced and easily shipped across the country or around the world. So the idea that's being tackled here is that in countries where the population is quite spread out, like the US, you lose a lot of electricity in the inefficiency of moving the electricity. So as it goes through the wire, you lose some of that as a function of distance the electricity has to travel. One simple solution to this is just move the source of the electricity closer to where it's being consumed. So that's the idea with the small modular reactors, is they can be deployed in many different smaller locations and put the source closer to the point where it's being consumed. And there are quite a few startup companies looking into these small modular reactors. One other thing I have to mention here is fusion. The general idea behind the physics is a bit similar but in reverse, where this time we have a hydrogen-2 and a hydrogen-3. They fuse together to produce a helium-4 and a neutron. And what you had before weighs more than what you had afterward. So you've again converted mass into energy. Right now under construction in the south of France is ITER, which seeks to be the world's first experimental fusion reactor, which produces more energy in total from fusion than the total amount of energy that's invested into the system to make the conditions just right for fusion. So in terms of commercial viability, fusion has a bit of a reputation for being always 20 years away from commercial viability. There is a lot more interest and research going on in the fusion realm at the moment. I still don't know whether we'll have commercial fusion in my lifetime. It's possible, but I'm not sure. But in terms of the long-term future, it definitely is something worth researching, because hydrogen is the most abundant element in the universe. So in summary, I hope I've made the good case that nuclear energy is clean and safe. It's extremely reliable. it produces a lot of energy, both in terms of the total amount it can produce for the whole world, as well as just the energy density of the fuel too. And also to keep in mind there is we're only using 0.7% of the uranium now. It would be even more, produce a lot more energy if we were using the other 99% as well. Nuclear plants, though, are expensive to construct, but at least in comparison to fossil fuels, they're a lot cheaper to operate just due to how cheap per unit energy, per gigawatt hour it is to produce that energy from the fuel. And again, we're only using 0.7%. If instead we're using all of it and we're able to use materials like thorium, this cost argument gets a lot more favorable too. The waste disposal problem is one which, from the science side, has more or less been solved, but from the political side remains a challenge. In the US, for instance, we do have a proposed waste disposal site called Yucca Mountain, but it's essentially been delayed and delayed and delayed due to politics. Hopefully, though, it will eventually be approved. And the future of nuclear technology is going to be even safer. Let us recycle our fuel and utilize even more of the material, which will ultimately reduce the longevity of that waste and allow us some flexibility, allow us to produce hydrogen as well as electricity, so nuclear can possibly follow the demand of electricity throughout the day. And that concludes the talk. Thank you, and I hope you enjoyed.